श्रीरामचन्द्र कृपालु भज मन हरण भव भयदारुणं श्रीरामचन्द्र कृपालु भज मन हरण भव भयदारुणं नवकञ्जलोचन कञ्जमुखकर कञ्जपदकञ्जारुणं श्रीराम 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 श्रीरामचन्द्र कृपालु भज मन हरण भव भयदारुणं कन्दर्प अगणित अमित छवि नवनील नीरज कुञ्जनं पटपीतमानहु तडित रुचि सुचि नौमि जनकसुतावरं श्रीराम 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 भज दीनबन्धु दिनेश दानव दैत्यवंशनिकन्दनं रघुनन्द आनन्द कन्द कौशल चन्द दशरथनन्दनं श्रीराम 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 धीरेना 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 सिरमुकुट कुण्डल तिलक चारु उदारु अङ्गविभूषणम् आजानुभुज शर चापधर सङ्ग्रामजित खरदूषणं श्रीराम 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 इति वदति तुलसी दास शङ्कर शेषमुनिमनरञ्जनं मम हृदयकञ्ज निवास कुरु कमादिखलदलगञ्जनं श्रीराम 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 धीरे धिं धिं तन धीरे धीरे धिं धिं तन धीरे धीरे धिं धिं तन धीरे धीरे नो श्रीरामचन्द्र कृपालु भज मन हरण भव भयदारुणं नवकञ्जलोचन कञ्जमुखकर कञ्जपदकञ्जारुणं श्रीराम 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 श्रीराम
This beautiful Ram Bhajan in the melodious voice of Basudhara was describing him as the merciful, the one who removes all fear. Fear goes when we feel supported by the one who can do everything, who's all powerful, and even more when we can identify ourselves with him, because then there is just that one. And when there is one, whom is that one to fear? For fear, you need at least two. And that's how ultimately all fear disappears in the mind of the devotee. And when the divine assumes the human form, comes down to this earth as an incarnation, as Rama and Krishna did, that apparently is to get rid of demons, to eliminate the demons, not only to punish the demons for the evil that they are doing, but also to let the others, the gods, and goodness in general, be able to do its job, to be able to function without being disturbed, without fearing the demons. But that is the apparent function of the incarnation of the divine. Sri Aurobindo has emphasized that if that is all that an incarnation had to do, then the divine could have done it by sending to the world a warrior strong enough to take care of the demons. The true purpose of the avatar or the incarnation of the divine on earth, according to Sri Aurobindo, is to take the consciousness of the human race to a higher level. So uh, that is the true purpose of the incarnation of the divine on earth, because after a certain degree of evolution, the human race is ready for taking the next leap. And it is to facilitate that next leap that the divine incarnates as a human being, shows the way, and then that process continues for another few thousand years. Now, turning to today's subject, that is the nervous system. Nervous system is one system about which we know more than about any other system in the body. And that's why we'll have more sessions. One could have an endless number of sessions on any system, but for the cardiovascular system, the respiratory system, and the digestive system, which are the major systems of the body, we had only 2 sessions each. For the nervous system, we'll have 5. So we know a lot more about the nervous system than about any other system. But then paradoxically, what remains to be known about the nervous system is also more than what we than in the case of the other systems. And that is because the nervous system has much more mystery hidden inside it. And in fact, that mystery gets a little easier only when we associate our knowledge of the nervous system with spiritual wisdom. That's because we look at the knowledge of the nervous system as something which will provide us answers to some basic existential questions, like how do we think, how do we decide what we actually do, and things like intelligence and memory and learning. Now, these are all subjects which are very fascinating, and there is always more to learn from the nervous system, as well as by associating the knowledge of the nervous system with the spiritual wisdom. Now, as in the case of the other systems, let's have a look at how the nervous system contributes to homeostasis, that is, providing a relative constancy of conditions which prevail in the fluid surrounding every cell of the body. It is this tiny amount of fluid, the private pond that every cell in the body has, which should have the nourishment available for the cells, oxygen, and the waste products should not accumulate there, and it should have the right degree of saltiness and acidity and so on. And every system is making some contribution to this. Now, how does the nervous system contribute? Nervous system contributes by coordinating the activity of different parts of the body. And for example, suppose we take exercise, we start consuming more oxygen, we start producing more carbon dioxide, and to maintain the constancy of the supply of oxygen and removal of this extra carbon dioxide that is being produced during exercise, the heart needs to work harder, the respiratory system needs to work harder. Now, who tells the heart to beat more frequently and more with greater force? Who tells the lungs to breathe more frequently and with greater depth? Now, it is the coordinating systems of the body that do that. And that's how the conditions of survival are ensured for every cell of the body. And we have seen that we have basically 2 coordinating systems, the endocrine system and the nervous system. And the 2 are in a way a little different, but in a way also closely associated. So when we talk about the different characteristics of the endocrine and the nervous system, it is primarily for convenience. And because this is knowledge which has been passed on to us from days when we did not know much about the interaction between the endocrine and the nervous systems. Now that we know more, the line dividing them is getting more and more fuzzy, but all the same, one can sort of have some idea of how these systems are different, and that also tells us why these two systems are necessary. The endocrine system pours the hormones directly into the bloodstream. These hormones reach everywhere, and therefore the action of the endocrine system can be more generalized. Whereas in case of the nervous system, we have nerve endings reaching a specific part of the body, and therefore the action is more specific, and the change will come about anywhere, only at those places where the nerve supply is uh, taking those messages. But at the same time, in the case of endocrines, also the action is not as generalized as one may assume, because the places in the body where the hormone will act are only those where the receptors for that hormone are present. Secondly, the endocrine system takes a little longer to start working, but once it starts working, it takes time for it to switch off. And even after the endocrine gland has switched off, the hormone will continue to be in circulation, and therefore the action is likely to last longer. Whereas in case of the nervous system, the on-off switch is much more efficient, and therefore one can switch on the action of the nervous system and switch it off more easily. Now, this action can be compared, a bit to the action of the two systems can be compared to some extent with the difference between, say, a blog and an email. A blog is something which you throw into the internet and then anybody can see it. That is something like the way the endocrine system works. Whereas the nervous system is more specific. It's like an email. You send the message to one person or to a group of people, but still there is a great deal of specificity about who will be able to read this message. So that is one way we can look at the difference between the endocrine system and the nervous system. But both these are coordinating systems of the body, which ensure that the tempo of activity of different parts of the body is in keeping with the immediate requirements. And in fact, that is one way medical students are able to sort of learn quite a bit of physiology. Instead of knowing what happens in a particular situation, they try to think, what is it that will help the body in this particular situation? And if they use that as a guide, invariably their answer is right. That is exactly what the body does. And that's sort of something which is actually a roundabout way of thinking, but at the same time, it helps a lot without trying to remember things to be able to say what would actually happen in the body. And that's what makes physiology very interesting. Now, coordination needs basically one thing, and that is communication. Because if the response is to a change, first this coordinating system should be able to sense this change, which means it should be capable of receiving information from those places which matter in that particular situation. For example, if the body is responding to a change in the environmental temperature, then firstly, this coordinating system should be able to sense what type of a change is taking place in the temperature, or what is the type of impending change. Sometimes, there's also anticipatory action. So the system should be able to sense what type of a change is happening in the environment that's grown cooler or warmer. And then it has to have a processing unit, a place where the input from various places is put together, because related to the temperature may be some other types of information which also would be helpful to the body in responding. All this is put together at one place by this coordinating center, and then a decision is taken about what should be done, what should happen in a few selected parts of the body. And then a message should be sent to those parts of the body so that the activity of those parts can change to meet the requirements of the body, to do what will be good for the body, to maintain homeostasis, to maintain that constancy of the environment around every cell. So we need two types of communication: information coming to the processing unit from the place where the changes are taking place, and then The second type of communication from the processing unit to the place where the action actually has to take place. So we need this type of two-way communication. Now, in case of the nervous system, because there is a great deal of specificity of action, we can't just depend upon some sort of a chemical change to be experienced and then a chemical to be released. There has to be a greater degree of specificity which can be achieved through wiring, which means that there should be some physical structure which conveys this change to the processing unit, and another physical structure which then conveys it to the place where the action actually has to take place, which means that we need extensions, and structure is in keeping with action. We find that in the nervous system, the basic unit, the neuron, does have long extensions. For example, if the person has stepped on something sharp and the foot has to sense this pain and respond to it, then there should be some way of communicating this to the spinal cord and from there up to the brain so that the person can feel what has happened. So for it to be able to travel to the spinal cord from the foot could be a distance of more than a meter, and then another 1 meter or so from the spinal cord up to the brain. And then if the foot responds by withdrawing, then once again there has to be at least some extension from the place where the withdrawal is planned up to the foot. And this can again be several meters long. And in fact, there are nerve fibers which travel actually from the highest seat of the nervous system, that is the cortex, where we decide to do what to do with the foot. From there right up to the muscles which supply the foot. So there's a 2 feet long extension, you can say, which comes right from there up to the spinal cord, and then another one from the spinal cord up to the foot. So just 2 neurons, and this entire distance is covered. So long extensions can be there. So that is the type of structures that we have in the nervous system. These extensions are extremely fine, visible only under the microscope, but all the same, they are there. And we have a very large number of them to make possible the variety of actions that we have in the nervous system. Our nervous system has 10 raised to the power 11 neurons. That's the rough estimate, which means after 1, you put 11 zeros, and that's how you get the number of neurons. And then further, these neurons have to be interconnected. And on an average, each neuron has 1,000 connections, which means that we are dealing with 10 raised to the power 14 connections between these large number of neurons, which makes all the action possible. Now, let's turn to the whiteboard to have a look at some of the things that I have been talking about. Now let's see how a nerve cell looks. Typically, we draw a nerve cell something like this. Now, this is the nucleus. Every cell has to have a nucleus to control its activities, to direct the type of proteins which will manufacture, and depending on the type of proteins it manufactures, it performs different functions at different to the different levels and so on. So whatever the cell does and the way it behaves depends primarily on what is happening in the nucleus. Then you have these processes, and we can say that there are two types of processes: those which receive information, receive from the periphery or receive from other neurons, and these which receive are called the dendrites. And then there is this extension which takes information away from this nerve cell. This is called the axon. And then you have these endings which may be branched, and each branch then may go to another neuron. To convey the message. So it means that there should be a transmission possible from this nerve cell to another nerve cell, and what will receive will be the dendrites of this neuron. So it will be the dendrites of this neuron which will receive the information from this neuron. So this is how we draw a typical neuron. But all neurons don't look necessarily exactly like this. They come in all types of shapes. Some of them may be like this, and some of them may be like this. This is the place which the cell body which has the nucleus here. This is the cell body which is the nucleus. So they come in all types of shapes, and they form all types of networks. There may be simple networks. This is how we draw a neuron typically, just a circle and an extension from there. So there may be networks like this, which are relatively simple, which are more or less sort of just for simplicity that we draw them like that. But otherwise, there would be, there is much more complication. Some of them may have a tendency to diverge, so that the information spreads far and wide. And so on. Some of them may have a tendency to converge. Bringing diverse inputs, converging at one point. Some of them might have more of a reverberatory type of a circuit. So that after bringing the information from many other sources, you may you end up giving some feedback to this neuron from wherever this message has gone. So they may have a reverberatory character. So we have all types of networks. But one of the basic sort of organizations in the nervous system is what is seen in a reflex action. And that's what we shall see. Uh, in the nervous system, we basically have the central nervous system. The brain, and the spinal cord. and this is the cerebellum. Hmm. So this is the brain, and this is the brain stem. See the junction between the brain and the spinal cord. So the reflexes are organized in the spinal cord and in the brain stem primarily. And so what we shall do is we shall have a look at a section of the spinal cord. So if we cut it like this, then how it looks, and then use that to understand what a reflex action, how a reflex action is brought about. So if we cut the spinal cord transversely, we find that it has an appearance somewhat like this. This is the backside, and this is the front. And within that, this division that I've shown is because this part has a greater collection of cells, that is cell bodies. We saw in the neuron, we have the cell body and then an extension. So these cell bodies are concentrated here, whereas this part has more of fibers. Fibers means these extensions. These extensions are called the fibers. And this has more of cell bodies. And since the fibers are relatively white, this is sometimes called white matter. And the place where we have the cell bodies, they are relatively gray. So this is the gray matter. It's from there that we get this common term, when we try and sort of a stupid person, we sometimes say it has no gray matter. No gray matter means, because this is what we call and the gray matter in the spinal cord, where there's a concentration of the cell bodies of the neurons. Now let's see how a reflex action is organized. Now for the reflex action, the nervous system, the spinal cord first has to receive information from the periphery. And that information comes through this nerve fiber from a receptor. And this is bringing this message about whatever type of change has taken place. And the cell body of this neuron is typically just outside the spinal cord, near it. And the simplest reflex will be one in which this then conveys this information to another neuron, which then brings it to an effector. So this is the receptor, and this is the effector. So this is how a reflex action is organized, the simplest reflex action. Now let's have a real example of a reflex action to understand it a little more. Say this is the arm and this is the hand. And the finger has accidentally touched a needle. Now, this is a painful stimulus. And what happens is that a group of sensory nerves will draw just one fiber, conveys this to the spinal cord. And normally, there would be at least some interneurons interposed between this and the cell, which finally goes and supplies the muscles of the arm, as a result of which the person will withdraw the hand. So the person takes the hand away reflexly. And this happens because this neuron say this is a muscle cell, conveys it to the muscles, which will help us take the hand away. Now, this is the basic reflex. And this type of actions are typically inborn. Even a newborn baby, if it gets a painful stimulus like this, will take the hand away. So this is something inborn, and it is stereotype, which means that every time the finger experiences this type of a painful experience, the action will be exactly the same. The hand will be taken away. And thirdly, it is involuntary. Which means that it does not require the intervention of willpower. And without thinking, without wishing to do so, without intending to take the hand away, the hand just moves away when it touches this pin or needle. And the fourth is that it is processed. All the processing is at relatively lower levels in the spinal cord or in the brain stem, but the processing is always at a level below the cerebral cortex. Cerebral cortex is that part of the brain which is concerned with conscious perception and willful action. So the stimulus has not yet been perceived consciously, and we have not decided to withdraw the hand, yet the hand is withdrawn. And it is this simple circuitry at the level of the spinal cord which makes it so quick. However, the matter doesn't end there. The stimulus which came from here is also conveyed through another set of nerve cells to the highest parts in the brain. That is the cerebral cortex. And in the cerebral cortex, then it spreads in different directions to other neurons. And the result of that is, firstly, that we become aware of the painful stimulus. So this awareness, in fact, comes a little later. It has a longer circuit to follow. We realize what has actually happened. And another thing which can happen as a result of this is that a willful action may also be taken. For that, then then another neuron would come. And lead to some other types of actions. For example, suppose a person has accidentally touched a pin like this. Then the withdrawal of the hand is reflex. It's a quick response. But then when the person becomes aware of the painful stimulus, knows why it has happened, the person may decide to remove the pin from there and keep it somewhere else so that it doesn't happen to him again. Or if suppose he has stepped on a stone or a burning piece of coal, and the foot has been withdrawn, after the person realizes that I have stepped on this and that is why it happened, the person may decide to move it aside so that nobody else steps on it. Or the person has slipped on a banana skin. The initial responses will be such that the impact of the fall is minimized. Those are reflex actions. But once the person has become aware of why it happened, what has happened, and so on, how it happened, then the person may decide to remove that banana skin, throw it in a dustbin so that nobody else can slip on it again. Now, those are voluntary actions. So voluntary actions can follow, and that's why we require more complex circuitry here. And but all the same, there is a certain basic circuitry which ensures a protective response, which is inborn. The person doesn't have to learn it. Removing the banana skin and keeping it aside is something which is learned later in life. So that's a learned response. But this reflex is an inborn response. In that voluntary response which comes later, which is learned, there can be also a lot of variation, which means that one thing, maybe one type of thing may be thrown into the dustbin, whereas it's a burning coal, you may decide to pour some water over it to cool it down. Now, what to do in which situation is something which is not stereotyped. So there is what you are doing is not the same for a burning coal as compared to, say, a nail or a stone. You're handling, or a banana skin. You're handling all these different types of stimuli for which the response may be reflex response might be quite similar, but you're handling it in different ways when it comes to the voluntary response, which follows this. And this type of voluntary action, which depends upon conscious perception, for that, the information about the stimulus has to go all the way up to the cerebral cortex, the highest reaches of the nervous system. So that is the difference between a reflex action and a voluntary action. Now let's have a look at how this information is conveyed from one neuron to the next, because we can see that is something basic. The entire circuitry involves a large number of neurons, but one thing which is repeatedly happening is that one nerve cell or neuron is conveying whatever information it has to pass on to another neuron. And let's see how that happens. So basically, we have to see what is it that is happening here so that the message is transmitted. Now, this junction is called a synapse. And this transmission is called synaptic transmission. So this is the junction. So we have to see what is it that happens here. And what happens here is very similar to what happens at the neuromuscular junction. We've already seen, how the information is conveyed from a nerve which is supplying a muscle to the muscles itself. And something similar happens here also. So what we'll do is for understanding it better, what we'll do is we'll draw the nerve ending enlarged. So this is one neuron, the axon that is bringing information. And this is the second neuron to which it has to convey. And this is the receiving extension, the dendrite of the next neuron. So how is it conveyed here? The information comes along this axon in the form of an electrical impulse. And when this electrical impulse reaches the end, it makes these balloon-like structures, the vesicles, which contain a chemical, move closer to this and release this chemical into this gap at the junction, into this gap, the synaptic cleft as it is called, this junction between neuron 1 and neuron 2. Now you can see that the process is very similar, and the language used is the same, the electrical language and the chemical language. So the information comes along in the electrical language of impulses, and it is translated here into chemical language. In the chemical is released in this at this junction, and then this is again translated into an electrical language. There's an electrical change here. So once again, there's an electrical change here. Now the degree of this electrical change depends upon the amount of chemical released. And see, if the chemical released is less, then the change may be this much. If the chemical released is more, then it may be this much. And there's a certain threshold, that is, there's a certain level beyond which, if there's a change, then it leads to a sharp response. And the sharp response is what we call the action potential, and that is then conveyed here. Otherwise, these small changes which do not reach the threshold just lead to that type of a change. It is not entirely a waste. It makes this nerve cell more sensitive to inputs coming from other areas or other neurons, but that by itself does not lead to the action potential. So, but there is this electrical change, and if it crosses a certain threshold, then an action potential, that is a set of nerve impulses, are conveyed along this. And say this is the cell body, then it will travel along the axon. So this is how the transmission takes place here. But as compared to the nerve muscle junction, where things were relatively simple, we had only one neurotransmitter, that is acetylcholine. Here in the nervous system, we have a large variety of neurotransmitters. So the neurotransmitter may be acetylcholine, but it could be also adrenaline, it could be dopamine, it could be serotonin, or it could be GABA. So the large variety of neurotransmitters. Secondly, it is not only neurotransmitters which are released, but there could be also another set of chemicals which we call neuromodulators. Neuromodulators will not actually lead to a transmission of the message. They can only increase or decrease the sensitivity of the next neuron to the stimuli that are coming from the nerve cell. So they can increase or decrease the sensitivity to these neurotransmitters. Another complication is that all neurotransmitters do not necessarily lead to an excitation of the next neuron to which the information is conveyed. There can be excitation or stimulation, or there may be inhibition. So as a result of the message coming from one neuron to the next, As a result of this transmission, this neuron may be excited or inhibited, and the sensitivity of this to this excitation or inhibition may be altered by the neuromodulators coming from here. Not only that, the same neurotransmitter may lead to excitation at one neuron, and in another case, it may lead to an inhibition. So all these things are possible, and that is what makes the action of the nervous system very versatile. Now let's try and understand a little about something which is interesting, not always talked about while talking about the nervous system, and that is how is it that such an elaborate nervous system has really evolved. The evolution of the nervous system. Now, if you look at a single-celled organism like an amoeba, we have seen that it can also sense a change in the environment, food or danger it can sense, and respond appropriately by consuming it, moving closer to it and consuming this food, or moving away from it if it spells danger. So it can respond to both stimuli which attract and stimuli which repel it, stimuli which facilitates its survival and stimuli which threaten its survival. It can respond to that. But then as the organisms became more complex and we had multicellular organisms, then what happened was that there were some cells in this multicellular organism. Say if we draw for simplicity this multicellular organism, there were some cells which got specialized in responding to the surroundings and in taking appropriate action. And these cells, what was their basic change? They became more sensitive to the surroundings than the remaining cells. So there was an increase in the level of sensitivity. The cell as a whole was sensitive in case of a single-celled organism. Here, some cells specialized in having a greater sensitivity. This was the beginning. Then next what happened was that these sensitive cells started forming clusters. And that is how some simple networks built up. So they started forming clusters. And then after these clusters were formed, what happened was a major change that happened was that the organisms remained not just a blob, but acquired bilateral symmetry. That is, you could draw a midline, and around that there were the two sides, the left side and the right side, and these two sides were almost exactly the same. So it acquired a bilateral symmetry. And when that happened, then another thing happened. These clusters of cells, which were more sensitive, they concentrated at one end and they were less numerous at the other end. And the end at which they were more numerous was the head end, and this was the tail end. And the animals started moving in this direction. And the result was that the concentration of these clusters at the head end ensured that the head will be able to sense more accurately food, danger, and any such thing to which the organism needs to respond and take appropriate action. So there was a further specialization, as you can see, at the head end, these were four. Another thing that happened was that these structures near the head end, they got further specialized. They were not just more sensitive, they became more sensitive to a specific set of stimuli. Like say, some of these cells were particularly sensitive to light, some were particularly sensitive to sound, some were particularly sensitive to a chemical change. And therefore, now the organism could sense a variety of stimuli selectively and specifically, and there were cells which were specific to a particular type of stimulus. And you can see that that was the way ultimately these structures which were particularly sensitive to light became eyes, and these cells which are particularly sensitive to sound became our ears, and those which are particularly sensitive to chemical change became the receptors for sensing taste and smell. And all that happened at the head end. And that one can easily understand how it is more useful, because that is the direction in which the animal is moving. That is the direction in which, if the animal is able to sense, then the animal as a whole can take appropriate action. Then what was the next step? The next step was that if at the head end these clusters were useful, then a more complex circuitry would be still more helpful. And that's how the size of these clusters at this end started growing bigger. So the animal started having a distinct head, which was much bigger in these animals than the rest of the body. So the head started growing so that it would accommodate a larger brain. A larger brain could do much more than a small brain, and that's how the size of the brain started growing. And further, what happened was, within this larger brain, there was a specialization at the head end, as we saw. And within this head end, what happened was that to start with, this brain had regulatory centers for the functioning of the heart, for respiration, basic functions which are essential for survival, so that these functions which are essential for survival could be coordinated much better. That is what happened in this bigger cluster of cells. Then, with further evolution came another growth which could give the animal, the activation of which could give the animal different types of feelings or emotions. And this was no less important than the basic functions like beating of the heart or breathing. This was no less important because by coupling survival to feelings was essential, created in the animal not only the capacity to live, but also the urge to live. Now, having the regulation of the heart and the breathing, or say feeding function, when the animal is deprived of food, it gets hungry. Now that also gets organized here. But then if, so the animal eats. But then that is not enough. If lack of food also leads to a sense of misery, then the animal develops a motivation to look for food, and that improves the survival. And when the animal finds the food, not only is that misery removed, the animal feels happy. So coupling happiness with getting food and misery with deprivation from food made it ensured that the animal will actually search for food, and that improves the survival. So feelings came. And this coupling, we can see, helped in survival to escape the misery due to deprivation of food or not having a mate, and in anticipation of the pleasure which the animal will get when the animal finds food or a mate, ensured that basic functions like food and sex, they would be looked after by the animal. The animal would be motivated to take care of those needs. And then with further evolution came another growth, which it made it possible to thinking. And this is the part that we call the cortex, the cerebral cortex, cerebral referring to the brain in general, and this outermost layer is the cortex. Now, if we look at the brain of different animals, we find that this type of a basic organization is there in very primitive creatures also. This is fairly well developed in reptiles. And amphibians, like say snakes and frogs. But this is hardly there in these animals. But then you find a thin layer of cortex even in these animals, but the cortex becomes really prominent in the mammals. cats and dogs and elephants and lions and tigers and so on. And the way the human brain differs is primarily in having a very big cortex. If you look at the brains of different animals, you find that this basic structure has hardly changed. In human beings, it's hardly different from that in a very primitive organism. When it comes to feelings, again, we basically have a brain similar to the reptiles. But when it comes to the thinking part of the brain, we do much better than all the other animals, including mammals. So you can see a bigger brain, particularly a bigger cerebral cortex, means more of those unique abilities which we associate with human beings. And therefore, the general trend was to have bigger brains in evolution, to be able to house a more complex circuitry, to be able to house a circuitry which was associated with the functions which were not well developed, or which had not yet developed in primitive organisms. So this is how we can look at the evolution of the brain. And one of the things we find is the size. And in general, the bigger the animal, the bigger will be the size of the brain. And we find that the biggest brains probably existed in dinosaurs. But then that doesn't necessarily mean that the dinosaurs were extremely intelligent. The reason is that the dinosaur also has a very big body. And therefore, a great deal of this brain has to be dedicated to regulating the movements of this large body. And therefore, a larger size did not necessarily mean better function. And therefore, we find that after that, the trend in evolution was to have, in fact, smaller animals, not animals as big as dinosaurs. There were many other reasons also why dinosaurs became extinct. One obvious reason would be that they needed too much food. And therefore, the supply was very difficult to get the amount of food that they needed. But then apart from that, they were not very intelligent also, probably because although the brain was very big, much of it was dedicated to the basic function of just moving the body itself. And therefore, the trend was to have smaller animals like whales and elephants. Now, these animals also have pretty big brains, but relatively small bodies. And therefore, they are able to think much better than probably dinosaurs could. They have better cortical function. And we find that in this case of these whales and elephants, etc., what has happened is that the brain may be smaller than that of a dinosaur, but then the body is still smaller comparatively, and therefore so much of the brain doesn't have to be dedicated to controlling this body. A lot of it can be used for functions like thinking. So in other words, we can say that there's a change in the brain-body ratio. That is what is crucial to how an intelligent animal can be. And so a better brain-body ratio, a higher brain-body ratio is what essentially is at the root of this evolution. And I'll stop sharing this here and go to the PowerPoint, where we'll continue this a little further. So this is the brain-body ratio. So in case of the whale, the brain weighs 9 kilos, the body weight is 90,000 kilos. Of course, there are many types of whales, but I mean, this is a good approximation of an average whale. So the brain-body ratio is 1:10,000. In case of the elephant, the brain is smaller, 6 kilos, but the weight is 6,000 kilos. The ratio is much better, 1:1,000. So you can expect an elephant to be more intelligent than a whale. In case of a gorilla, one of the apes, the brain weight is only half a kilo, much less than an elephant, but then the body weight is only 125. So the ratio is 1 is to 250. In case of the chimpanzee, 0.4 and 60, 1 is to 150. And that's why we find that the chimpanzee, in fact, is an extremely intelligent animal. In case of monkeys, some monkeys, the brain-body ratio may be even better, 1 is to 20. But then the brain is only 0.3 kilos. The better ratio is because the body is very small, only 6 kilos. And again, this monkey cannot be extremely intelligent because there's a limit to what you can pack in a small brain of only 0.3 kilos, which means that you need a little bigger brain to be able to have that complexity. Man has achieved a sort of a golden mean of a brain around 1.5 kilo, body weight of 60, and the ratio of 1 is to 40. Much better than in most animals. May not be as good as in a monkey, but all the same, a big enough brain to house all the complexity that we have. Now, how about the dolphins? Dolphins may have a brain which is slightly bigger than that of a man, a weight a little less, and the ratio could be much better than in a human being. Instead of 1 is to 40, here we have 1 is to 30. Does it mean that the dolphins are more intelligent than human beings? Questionable, but certainly dolphins are extremely intelligent creatures. But then along with this, something else also has been happening, which has ensured that brains like those of man and dolphin are better than those of other animals, apart from growth in the size. Another thing that has helped is that there is also an increase in the convolutions, that is the folding. And the surface of the cerebral cortex shows all types of folds, and that increases the surface area. Larger the surface area, more the nerve cells that can be accommodated, and also more the connections that are possible. So increase in the number of neurons by having these folds, having more connections is another thing that has helped these animals become more intelligent. Now let's turn to the dolphins and see what all they can do. They can recognize themselves in the mirror, which most other animals can't. They can learn to use a keyboard to request for a toy. They have distinct personalities and they display ethical behavior. Dolphins have been known to help sailors protect them, show them their way to safety, and they can understand even our complex gestures. And therefore, it has been sort of questioned whether dolphins are just as intelligent or less intelligent, and also that should we not be treating them much better? Since they show such ethical behavior towards us and seem to love us, we sometimes respond by keeping them in captivity in aquariums, make them perform all types of things to entertain the visitors, and in some cases, they are also killed for various reasons to get this thing or that. So, therefore, people have, in fact, talked about developing more ethical behavior towards animals in general, but particularly animals like dolphins. Now, what is it that is unique about the human brain? Because human beings certainly have been able to dominate the planet the way even dolphins have not been able to. One of the things is speech. Speech gives us the ability to express ourselves in a very versatile manner and communicate messages which it may not be possible to do otherwise. And speech is something which so far no animal has been found to have the way we have. Second thing that has helped is cerebral asymmetry. This also no other animal seems to have. Logic and mathematics concentrated on the left side of the cerebral cortex, and abstract thinking, art, music, and creativity on the right side. Now, this leads to economy of space, because when it comes to sensing a stimulus coming from the hand or the foot, we need it on both sides of the brain. Or if we need to have, say, control over the musculature of the body, we need to have it on both sides because the left side and the right side both need to be controlled. But when it comes to things like logic, mathematics, or art and music, they don't have to be on both sides. They're not in terms of sides. They are for the person as a whole. And therefore, they can have this division of one thing being more concentrated on one side and another on the other side of the cerebral cortex. This leads to economy of space, which means that the same sized brain now becomes more effective because of this specialization of the two sides of the brain. So these two things, speech and cerebral asymmetry, is something that seems to be unique when it comes to the nervous system, but to the brain of the animal. So human beings, this is something which even dolphins don't seem to have. And that may be one reason why, in spite of a better brain-body ratio in dolphins, the dolphins perhaps are not as intelligent as we are. They're extremely intelligent, they're smart, but all the same, human beings have been able to do better than other creatures, perhaps because of these two basic reasons. Now let's look at the structure of the brain. This is the cerebral cortex, a thick cerebral cortex, under which we have the reptilian brain. And this is the structure that joins the left and the right side of the brain, because although they may have some specialization, they also need to have an interaction and coordination. So we have this joining. And what is not seen here is on either side of this joining structure, the corpus callosum, is a hollow space. And in that, this hollow space travels throughout the central nervous system. This hollow space enters into this hollow space here and then into this hollow space here, and this continues as a canal throughout the spinal cord. This hollow space has what we call the cerebrospinal fluid. And the cerebrospinal fluid performs functions similar to the interstitial fluid or this intercellular fluid, the fluid between cells in the rest of the body. Some of these functions are performed by this fluid here. What happens is that in these hollow spaces in the brain are a bunch of blood vessels which filter this blood, and that is how we get this fluid here. And this filtration is taking place from arteries. So therefore, this has nourishment and oxygen at the same level as in the arterial blood. And therefore, this can meet those requirements for the brain cells. And how does it meet those requirements? Here, at this point, we have those tiny openings, which then lead this fluid to a thin space around the brain as well as around the spinal cord. So it travels up and down. And then what has gone down comes up again, so that all the fluid is then back here and gets absorbed into the venous sinuses, that is large venous chambers, large chambers of venous blood here, so that like the rest of the blood returning in the veins, which has less nourishment and more of waste products, this fluid also then gets here. So this fluid keeps getting formed here, keeps circulating, and keeps getting reabsorbed. So this is the cerebrospinal fluid, which meets the same type of functions, providing nourishment. And why does the brain have this type of specialized arrangement? This is one arrangement. The other arrangement, which does some of these functions, are the cells which are interposed between neurons throughout the brain, called the neuroglia, neuroglial cells. So the brain has these specialized arrangements for looking after its nourishment, partly because, of course, it's a very vital structure and therefore it needs to be well taken care of, partly also because it shields the brain from many toxic substances in the blood, creates a sort of a blood-brain barrier. So everything that is there in the blood does not automatically reach the brain. It goes through this selective process, which has mechanisms for not letting the harmful substances pass. For example, bilirubin. Bilirubin does not pass into these structures. So even if the person has jaundice, bilirubin, which could be harmful for the brain, does not get into the brain, except in infants, because in infancy, particularly newborns, the brain barrier, blood-brain barrier is weak, and that's how it's able to get in here and can cause brain damage. And that's how if a child has neonatal jaundice, that is jaundice at birth, this can lead to brain damage. But if an adult gets jaundice, that does not lead to any brain damage. That's because of this shielding of the brain through this blood-brain barrier. So here we have the highly evolved mammalian brain, more evolved in human beings than in other mammals. This ring-like structure, which is the one that takes care of feelings. And this is the brainstem, which has the basic structures for regulating cardiac and respiratory functions. And this is a part which is particularly for coordinating the activities of our musculature, so that we don't have to always think activities which we perform habitually, which are voluntary in nature, which depend upon the use of willpower, can become habitual to us, so that we don't have to use the cerebral cortex for controlling those activities. The things like swimming, cycling, which to start with may need conscious effort, but after that they don't need any conscious effort. We are able to perform them reflexly because of this structure, and also this structure coordinates the activity of the muscles so that the movement is smooth. So this roughly is the structure of this brain. And then over here at the base of this emotional part of the brain is the hypothalamus, where thoughts and feelings can all converge, and which regulates not only the autonomic division of the nervous system, but also the endocrine system, particularly through the pituitary gland, which is here. So the pituitary being regulated by the hypothalamus, and the hypothalamus in turn funneling the influence of the feeling part of the brain, and the feeling part of the brain being in constant touch with the thinking part of the brain. We find that it is through this tiny little structure, the hypothalamus, that eventually the effects of our thoughts and feelings get disseminated throughout the body and lead to so many types of effects throughout the body. So that's how thoughts and feelings can affect all parts of the body in various ways. And that's how we have this intimate mind-body connection, the physical counterpart of the mind-body connection. This is the spinal cord, and we can see the nerves coming in and leaving from here. And the spinal cord is lodged in the vertebral column, and this is the front, this is the back, and we can see some of the nerves entering the spinal cord, some of them leaving the nerve fibers, leaving the spinal cord, and we have by the side of this vertebral body the sympathetic chain, and these are the enlargements in that sympathetic chain, bigger clusters of nerve cells, which we call the ganglia. This again a cross-section of the spinal cord, the back side, the front side, the gray matter and the white matter. This is a typical nerve cell, the cell body, the nucleus, the dendrites which receive information, the axon which conveys the information, and this is a picture under the microscope, and this is the end of the axon, and then these axon terminals or these branches which can transmit information to other neurons, or in case of terminal neurons, to a gland or a muscle. And gratitude to this Dr. Ryan Grabowski's book, Principles of Anatomy and Physiology, from where all these realistic pictures have been taken. Suggested reading, this popular book, The Human Machine, and these two textbooks, Fundamentals of Physiology and Understanding Medical Physiology. And this is the place where I stay and work, and from where I'm speaking. You're all welcome here. It's open to all of you. For any questions or comments, please do not hesitate to drop an email to yes@yesspirituality.com. Gratitude to the Mother and Sri Aurobindo for making these sessions possible. And thank you all for being there. Any questions?
Not yet.
If there are no questions, then maybe I can touch on something which is always a source of confusion. Uh, when we study the nervous system uh, using the a scientific sort of approach, then the impression that sometimes generated is that it is the uh, physicochemical changes taking place in the neurons of the cerebral cortex that leads to consciousness, that is, our becoming aware. Uh, but however, we'll go into this in detail in some of the subsequent sessions also. However, what we miss is that when it comes to the scientific understanding of these things, there is a black box of ignorance, which gets overshadowed in the large amount of knowledge and all the technical terms that we use. For example, if we see a flower and the information is, we know all in great detail how the information is conveyed from the flower to our eyes and then our eyes to the brain, and in which parts of the brain get activated when we actually perceive the flower. And we feel that somehow this is what is leading to perception. But the black box here is that the physical chemical changes, that is electrical changes and the chemical changes, which are alternating with each other, which is happening in the nerve cells, ultimately activates a certain part of the brain, which we associate with the visual function. But then that is only a physicochemical change, whereas what is experienced is a subjective experience. How is it that this physicochemical change leads to a subjective experience? That is the black box which science does not know anything about. Then, after seeing the flower, that's not the end of the story. I say to myself, what a beautiful flower. I want to have it. And then I decide to pluck this flower. Now, this planning, that is, I want this flower and therefore I want to pluck it, is something subjective. How does this get translated into the physical chemical changes in that part of the brain, which gets activated and eventually leads to activation of those muscles which are involved in plucking the flower? So that is the second black box, which means that this link between the physicochemical changes and subjective experience or subjective thoughts, that is something which we have not been able to link in science. But in spirituality, there is an answer to it. And the answer is that the brain is not actually the generator of consciousness, it is only a channelizer of consciousness, which means that the consciousness is universal in nature, and we have got an equipment in the form of our brain, which is able to channelize a certain fraction of this consciousness. And that's how we are able to have this link. Now, this is on a miniature scale, something that the rishis perceived in the creation of the universe itself. To start with, we had a non-material entity, the divine, and then that decided to express itself in matter. So once again, there was a change from a non-material entity to something material. Now, these subjective thoughts and feelings and perceptions are non-material in nature, and there's a link between them and the physical structure in the nervous system. So this requires the same type of a leap in consciousness to be able to accept, which the rishi experiences while being able to see that link. And that is where spirituality is able to complete the picture of the consciousness. And in science, that remains a black box, which we cannot really decipher using the scientific approach, which depends primarily on observations which can be made at the physical plane. And therefore, this link between the subjective and the objective, or between the physical and the non-material, is something which we cannot link. Now, the equipment that we have, that has been changing as we saw through the course of evolution. Now, this has had at least two aspects. One is that if a greater fraction of that universal consciousness has to be channelized so that the animal can have a larger consciousness, so to say, or be more intelligent, or whatever we may like to put it. So to make it this brain capable of transmitting a larger fraction of the universal consciousness, naturally the brain has to be bigger and more complex, which means that the equipment has been designed from time to time to meet this requirement for a channelizing a greater fraction of this consciousness. Secondly, qualitatively also this has been changing because the fraction that is channelized is the one which was most useful for the survival of that particular animal. And therefore, in some cases, an animal which evolved earlier might have some functions which are much better developed than in the rest. For example, we cannot smell as well as a dog can. So for the dog's survival, probably that was important, and therefore that part of the equipment was better developed, which could channelize information about smell. In human beings, it was considered not so necessary. Man is so intelligent that it does not depend so much on the smell to find food. And therefore, for the human being, it was perhaps not necessary. And therefore, that part did not have to get that much space in the brain as in case of a dog. So that's how I know that economy of space has also been conserved. What each animal has been given is what was most necessary for the survival of that animal. So both qualitative and quantitative changes have been taking place. It's something like, the way a person may design a computer. If the computer has to work faster, if the computer has to be able to do more, then the those who have to design this computer, they come up with an appropriate processor, a processor which can come up with the right speed and the right degree of complexity. And then, using that hardware, we can develop a program, which is the software. Now, the same thing is there in the brain. The hardware has been in keeping with the requirements. The hardware has been developing in the course of evolution. The way the computer processors have evolved over time, they become more and more complex and become faster. They can do more. In the same way, the brain also, the master craftsman did the same. It kept designing a bigger brain when it was necessary. And when too big a brain itself became a hurdle because it was controlling too big a body, optimum brain body ratio was achieved, and so on and so forth, we saw. And then selectively, those characteristics got more space in the brain, which were more essential for the survival of that particular animal. So essentially, it's a question of the brain channelizing the consciousness rather than generating the consciousness.
Okay, there's this question. What is the reason for the numbness in one's legs or hands? And okay, first you can take this question.
This would mean defect somewhere in the sensory part of the nervous system. We call it sensory and motor. Sensory is what the information that is going to the nervous system. Motor is what is coming from there. And that actually will be the subject of the next session. So it can be at any level in the sensory system, which can lead to this type of a numbness. But some of the common causes of numbness would be in the peripheral nerves, and that may be because of a vitamin deficiency, like deficiency of this cluster of vitamin B1, B6, and B12. That could be one of the reasons.
And when we get pain, be it headache or leg pain, etc., is it the nerves that are hurting in the particular part of the body? How to keep nervous system healthy?
How to keep nervous system healthy, that is a broader question, in a way easier to answer. Use it or lose it. Keep using the nervous system, and it will remain healthier. So it means that basically we have to keep using it. About the pain, again, we shall talk a little when we talk about the sensory system. But when it comes to the transmission of a painful stimulus, we know the pathway very well, pretty well. And it means it starts with a stimulus, which may be outside or it may be inside. Outside, it may be, say, like a pinprick, as we were talking about, but the stimulus could also be inside, like, say, an obstruction in the biliary passages or in the intestine. So we have pain arising from within, we have pain arising from outside. And then why pain which arises from within the body also eventually makes itself felt somewhere on the surface of the body. For that, again, there are explanations available in terms of the neural pathways. But essentially, pain is a protective response. It's a warning. It tells us what is wrong, what needs attention. So it's on the whole a protective response. But then, like anything in excess, can be counterproductive. pain in excess can also be counterproductive, and it may not be necessary, and yet it is sometimes there. For example, cancer pain. Now it's one of the most severe pains, and yet doesn't seem to be necessary. The person, in any case, knows what the disease is, and the additional pain does not really help. But most of the time, the pain is a protective and useful response.
What causes brain tumors and how can we prevent that?
What causes brain tumors is what may cause a tumor anywhere else. There is a process for regulating the cell cycles, which means that the cell division keeps pace with the loss of cells. In case of the nervous system, there's not much regeneration. Earlier, it was thought there's no regeneration at all. But now we know that the division is relative, which means that nerve cells can also divide. And if they can divide, sometimes when the cell cycle goes wrong, they could also divide in much larger numbers at a much faster pace than they would. And this would particularly apply to some parts of the brain which do divide, like the coverings, etc. So there could be different parts of the brain which do divide, and when something goes wrong with this regulation of the cell cycle, the division could be at a much faster rate. And if the immune system of the body, which treats these dividing cells as foreign, cannot eliminate them, then it could grow into a full-blown tumor.
Is all for the questions.
That's all.
Yes, that is all for the questions. So maybe we can close today's session with a moment of silence. Thank you, everyone.